Welcome to the third test 3 the test 3 review over, I guess it's chemical quantities and reactions, gas laws, and maybe some other stuff. All right. So, what question would you like me to go ahead and start with? Sure. Okay, so I'm going to go ahead and zoom this in. Get a better, yeah, there we go. So it says, which of the following substances contains a nonpolar covalent bond? Okay, so first of all, we have to recognize that an ionic bond can be easily distinguished because there will be a presence of a metal or a polyatomic ion. So amongst these, which of these bonds are ionic bonds? A is one, sodium is a metal. What else? What other one is an ionic bond?
Ionic is metal and non-metal.
Yep. C. Now, when you say ionic is metal and non-metal, that is true 99.9% of the time, but also keep in mind you can have polyatomic ions like ammonium, NH4+, and that would act as a substitute for a metal. So NH4Cl, even though that's all nonmetals, that would still be ionic because NH4+ is a positive polyatomic ion. Does that make sense? That it would count as a metal, so to speak. Ionic really just means between a positive ion and a negative ion. Usually your positive ion is going to be some sort of metal, but it is possible to have a polyatomic ion that is a positive, but only has nonmetals in it. Really the only one you're going to see is ammonium. Okay, so we can rule these two out, A and C. So that looks like the remaining ones. The only way you can really have a true nonpolar covalent bond is if the electronegativities of the elements are the same. And that generally only happens if an atom is bonded to another atom that's identical to it. So electronegativities, let me actually pull this up. I don't know if you're going to see this or not, but it's going to be under here. Let's do this just because I'm lazy and I don't care. Here we go. If you look down at the electronegativity scale here, periodic table of electronegativity, you see the different electronegativities of the different elements. And you can see as you go across, they increase, and as you go up, they increase. So a nonpolar covalent bond will be between two atoms with the same electronegativity. But as you can see, there are very few atoms that have the same electronegativity. Like you don't usually get those kind of pairings where they're the same. So generally speaking, if you're talking about a nonpolar covalent bond, you're talking about an element bonded with itself, or a carbon with a hydrogen. Even though carbon and hydrogen are not exactly the same, they're close enough that they usually get lumped in with nonpolar covalent, even though they are in fact slightly polar. So let's look at this one. The only one of these that would be a nonpolar covalent bond would be which one then? B. And D and E are clearly actually very polar because they have hydrogen bonding. If you have an NH, OH, or FH bond, that's going to be hydrogen bonding. I don't know if you talked about intermolecular forces, have you? Okay, well some of you have, some of you haven't. Okay. Now, what about number 3? The answer to number 2 is B. What about number 3? What's that going to be?
Well, we would take off A, B, that.
Yep. A, C, and D. Clearly, those are not polar covalent because they have the same electronegativity. So then is between B and E. I'm hearing B and E. How many of you say B? Raise your hand.
I have no idea.
And how many say E? And how many you don't know? All right, a few of them. Okay. What kind of bond is NaCl? Ionic. If it's ionic, is it covalent? No. So the answer is going to be B. Now the truth is, NaCl is very polar. Ionic bonds are always extremely polar, but it's not covalent. It is ionic. And the difference is covalent means the electrons are shared between the atoms, whereas an ionic bond is where one atom completely rips the hydrogen or rips the electron away from the other. So you get a full positive and full negative charge. Like I said, typically it's actually usually pretty easy to tell. An ionic compound, a covalent compound will never have a metal, as far as you're concerned. A covalent compound will never have a metal. I say as far as you're concerned because that's actually not entirely true, but as far as you're concerned, you'll never see a covalent compound with a metal. However, so ionic compounds, like I said, 99.9% of the time, they're going to have a metal and then either a nonmetal or a polyatomic ion. And the only exception is ammonium NH4. That's the only one you're going to see. So if it has a metal or NH4 in front, probably it's ionic. It's going to be ionic. Any other questions?
Covalent never has a metal, and ionic is a metal and a...
Yep, and a metal and a nonmetal, yeah. Or a metal and a polyatomic ion. And of course, there's those 7 polyatomic ions that you're supposed to have memorized, which all of you have memorized, right? So I'm talking about nitrate. If you don't have these memorized, you may want to write them down. Chlorate. Hydroxide. What's the other one? Well, okay, there's sulfate, SO4, that's right. I was thinking of it. There's another negative one. Oh yeah, I remember what it is. Carbonate. But the other negative one polyatomic ion is acetate. And I'll put that at the top up here because it's C2H3O2. And you may also see it as CH3COO minus. But C2H3O2 with the -1 charge. And then and then there's phosphate, PO4, with a -3 charge, or 3 negative. And then the last one is the positive polyatomic ion you have to have memorized, and that's ammonium. As I said, ionic compounds can either have this, ammonium, or they can have a metal. It's going to be either ammonium or a metal and a nonmetal. That'll be what you'll see for ionic compounds. Okay, cool. So, clear as mud, right? No, just kidding. Yeah. That's carbonate. So yeah, there's top to bottom. Ooh, gosh, what the? I'm gonna have to zoom that over, or zoom out a little bit. Don't know why it's doing that. You can see it? Yeah, plus. There we go. That's acetate, nitrate, chlorate, hydroxide, sulfate, carbonate, phosphate, and ammonium. From top to bottom. Oh, and coincidentally, there's up on our website, there is a periodic table of ions. It has the polyatomic ions listed, and it also shows the ions of all the different whatchamacallit things. Actually, I'll show it to you. Huh? Look how cool this thing is. See? I'm gonna zoom in so you can see. Behold it in all of its awesomeness and glory. Shows you all the different charges, and plus it has the polyatomic ions. Make it easier for you to keep track. So there's all sorts of cool stuff up on the website. It's on the Learning Commons. Yeah. Okay. So back to our practice test. What question would you like me to go over next? Oxidation reduction. Let's see. Is there one on here? Ooh, okay. Yeah, let's do this one. Okay, so oxidation. Okay, so there's an easy way to think of this and there's a hard way to think of this, but you can think of oxidation as an increase in charge, okay? For the level of chemistry that you're working with, I mean, I know that there's like, Leo, the lion goes grr, loss of electrons, oxidation, gain of electrons, reduction, and all that kind of weird stuff, right? Or oil rig or whatever. But that stuff is confusing because reduction, when you hear the word reduction, what does that make you think of? Yeah, reduce. So like if you had a reduction in pay, would your pay go up or down? Down. Or if there's a reduction in the water level, it goes down, right? So why is it called reduction? It's called reduction because the oxidation number, which is, for all intents and purposes for your class, oxidation number is usually the same thing as charge. So you can think of oxidation as an increase in charge and reduction as a decrease in charge. So it's called reduction because the charge decreases, it goes down. It becomes less positive or more negative. Does that make sense? Reduction, decrease in charge, less positive or more negative, it goes down. So any element by itself, any atom by itself, does that aluminum right now have a charge? No. It only has a charge when it's part of an ionic compound. And does this bromine have a charge? No. It only has, so its oxidation number, its charge is 0. And this one is 0. So right now these charges are 0. Okay. But now when it reacts and forms aluminum bromide, what's the charge, what's the oxidation number of aluminum? It's 3 plus. If you look on your periodic table, it's a 3 plus charge. Now what is the oxidation number or charge of bromine in this case? -1, or 1 minus. Now we'll say this. While oxidation number and charge are not always the same, for this chemistry course, you will pretty much, I'm pretty sure you're always going to see it as that's the same thing, because oxidation number and charge is the same for ions. So, does that help at all? Not really? Any element in its elemental state has an oxidation number of 0. So any element in its elemental state has an oxidation number of 0. What do I mean by any element in its elemental state? So any element that's by itself. It's not with other elements. See, this bromine, it's only with other bromines. This aluminum is only with aluminum. So if it's by itself and it's not shown with a charge, because it is possible to be shown with a charge. Like if you draw like a, let's say for example, if I drew like a P3 minus here, well, if I draw it like this, then its oxidation number is 3 minus, because I've drawn the charge, and the charge is its oxidation number, okay? But if I wrote like this, if I wrote P4, and I wrote this, P4 solid phosphorus, there is no charge here. It's just an element in its elemental state, and therefore its oxidation number is 0. Exactly. Now, I could go into the more complex aspects of how you determine oxidation number for covalent compounds in difficult situations, but you're not going to come across that. Like, as far as you're concerned, what you're going to see in your course is that the oxidation number is going to be the same as the charge. And the type of oxidation-reduction reactions you're going to get are things like this. So it's sufficient to think of oxidation number and charge being the same thing.
And the only reason why the 3 positive and 1 minus is because you look at it on the periodic table.
Yeah, like for any ionic compound, the oxidation number of the ion is the same as its charge. Yeah, I mean, yeah, exactly, because it's a compound now. It's an ionic compound. Electrons have been exchanged. Exactly. Okay, so from here you can see that what has happened to the charge of aluminum? Has it increased or has it decreased? It increased, so this was oxidized. Oxidation is an increase in charge. Oxidation is the loss, but it refers to loss of electrons. Oxidation is loss of electrons, reduction is gain of electrons. Now here's the thing. For aluminum to go from 0 to 3 plus, has it gained or lost electrons? It's lost. Because electrons are negative, right? If you lose your negative attitude, you become a positive person. So that's kind of how it works. Like, you know. Yeah. So electrons are negative, so if you lose negatives, you become more positive. So you are losing electrons, but it makes more sense to think of oxidation as a gain in charge than to think of it as a loss of electrons. You have to do more mental gymnastics if you're thinking of oxidation and reduction in terms of the electrons. If you think of it simply as in terms of the charge or oxidation number, it's a lot simpler. Exactly. Oxidation is loss of electrons, yes. And reduction is gain of electrons. RIG, reduction is gain of electrons. But like I said, I don't really care for the oil rig or Leo the Lion goes grr or any of that stuff.
And so oxidation is loss of electrons and reduction
is gaining electrons.
Yeah. Can you say that again so I can write it down in my notes like that? Can you explain this in a way that I can write it down?
If you lose negatives, yeah. If you oxidation is an increase in charge. Reduction is a decrease in charge. And I'm going to go ahead and change colors. Reduction. So bromine goes from 0 to -1. That is a decrease. It is reduced. Because to reduce something means to make it less. And you're reducing the charge. Any questions on that?
like aluminum is just positive 3.
Yeah.
But aluminum can, I don't know how it goes positive 3 because it's 1, 2, 3. Number 15.
That's a good question. And I don't feel like answering it, to be honest with you. I'm just kidding. Here, I'll show you. So here, let me pull up this periodic table, and I'm going to download this so we can actually see it. But essentially, oh, what did I do? I did something terrible. Here. Yeah, periodic table. Okay, here it is. Okay. Oh. Alor, where is it? Okay. I'm going to download it again. Okay, open file. Here we go. Here, the reason I wanted to do this is because I want to show you something. On the periodic table, you have consistent patterns. Each one of these guys is going to lose one. If it becomes an ionic compound, it's going to lose 1 electron and become a positive 1 charge, right? Because it's going to try to be like the closest noble gas. If lithium has 3 electrons and it loses 1, it'll have 2 electrons. It'll be like helium, right? If sodium has 11 electrons, it loses 1. It'll be like neon, which has 10. And so on and so forth. All of these are going to lose 1 to be like the closest noble gas. Same thing with this column. All of them are going to lose 2 to be like the closest noble gas. Now, you guys have already done electron configuration and such, right? If you remember, when you go into the D block, remember what one of the issues with the D block is? You drop an energy level, right? The valence electrons are the ones that are involved in bonding. When you're adding electrons here, you're not adding valence electrons. So if you look at aluminum here, Aluminum only has 3 valence electrons. It's going to try to be like the closest noble gas possible. Is it going to gain 5 to be like argon? Or is it going to lose 3 to be like neon? Which one do you think would be easier? Losing 3. It's easier to lose 3 than gain 5. So this will be a +3 charge for aluminum. Now it does get a little bit more complicated as you go down, but it turns out that there is this little staircase of elements here that, despite the fact that they are in the transition area, because remember, transition metals refers not simply to, not simply to the D block, but it refers to all elements that can have multiple charges, right? So lead here can have multiple charges. Bismuth can have multiple charges. Tin can have multiple charges. These are transition elements. They can have multiple charges. But this little staircase here, I like to call it the magic staircase. I don't know why. But this little staircase here, it only has 1 charge. So, and it actually has a very convenient pattern here. Silver is always a +1. Zinc and cadmium are always +2s. And aluminum and gallium and indium are always +3s. So these guys are always +3s. So you have 1 + 1, 2 + 2s, 3 + 3s. So it's really easy to remember, really easy to kind of keep in your mind. But these guys, they don't get Roman numerals when you name them, precisely because they do not have multiple charges. They only have 1 charge. So that's how you can figure out whether or not something ought to, or what charge something ought to have. Furthermore, if you had wanted to, you could have also looked at the test and see how it says Br3. Well, from the periodic table, you should be able to identify that bromine here is going to gain 1 electron and be like krypton, so that's going to have a -1 charge. In any ionic compound, the total number of positive charges has to be equal to the total number of negative charges. So if I have 3 bromines, each with a -1 charge, that's a total of -3, right? So that means that aluminum has to balance that with a +3. Ionic compounds, the total positive always equals the total negative. Well, technically speaking, that's something you should have already learned. I know that some professors don't explain it that way, but they really should. I mean, I can make one up. You want me to make one up and you can try it? Oh, well, so here you see that aluminum was oxidized, right? And bromine was reduced, right? So that means A. Now here's the thing. One thing to note. Aluminum bromide, the product, is not oxidized or reduced. Products can never be oxidized or reduced. Products are the result of oxidation and reduction. So if it asks you what's oxidized and what's reduced, you must look at the reactants. You cannot look at the products. Products are not going to be the answer. Only reactants can be oxidized or reduced. So automatically that makes B, C, and D non-answers. Make sense? Cool. All right. And you wanted another example? All right, let's make one up. Let's do this one. Well, okay, no, that's going to be hard. Okay, let's try this one. Okay. Gosh, I'm having a hard time thinking of one. Yeah, let's do this. I'm trying to keep it relatively simple. All right, there you go. So take a second to work that one out, and then we'll go over together.
No, I'm
Ready? All right, let's do it. All right, who wants to volunteer an answer? Go ahead. Oxygen is reduced. Oxygen is reduced. So they originally both start out as 0, but on the other side, magnesium has what charge? A 2 plus, and oxygen has? Yeah, 2 minus. So magnesium increases from 0 to 2 plus, it's oxidized. Oxygen decreases from 0 to 2 minus, it is reduced. And actually, that's one of the reasons why they call it oxidized. It's not that oxygen gets oxidized, but other things get oxidized because they react with oxygen. Does that make sense? Oxygen tends to steal electrons away from things because it's electronegative. So when it steals electrons away from something, it causes their charge to increase and thereby oxidizes them.
So, in the equation whatsoever, if I got plus 2 for the first one, it would be but negative for that second one. Did you say something about how they have to like do each other or something like that? You were telling me, right?
Well, for an ionic compound, the total positive must always equal the total negative.
That's what I meant.
Yeah.
I feel like Dr. Mo's going to do it.
Okay, well, I'm going to throw this one at you, even though I haven't shown you how to do it, but we're going to work it out together. Okay, so this is a combustion reaction. So now here's the interesting thing. Basically, the universal overarching rule with regards to oxidation number is that an atom will, whenever an atom is bonded with other atoms, the most electronegative atom is going to steal the electrons it wants. The most electronegative atom is going to steal the electrons it wants. So in this case, how many does it want? Enough to fill its valence shell. Between hydrogen and carbon, which is more electronegative? Carbon. And so carbon's going to take what it wants. Now carbon has how many valence electrons to start with? 4. So it's going to steal 4 electrons from the 4 hydrogens. And therefore, carbon's going to have an oxidation number of -4. Now, each hydrogen is going to lose its 1 valence electron, right? So that means its oxidation number is going to be +1. And generally speaking, when you look at other tables of rules for oxidation number, you'll see that hydrogen is always either a +1 or a -1. The vast majority of the time, it's a +1 because it's usually bound with things that are more electronegative than it. So basically, hydrogen's a +1 with nonmetals and a -1 with metals. And it rarely bonds with metals. So then oxygen here has what oxidation number? 0. Now, the hydrogen over here is with an oxygen. What's its charge going to be? What's its oxidation number going to be? Well, so which is more electronegative, oxygen or hydrogen? So oxygen is going to take the electrons it wants, which means it's going to be what charge? -2. And that's another thing. Oxygen is almost always a -2 charge. There's a very few exceptions. If it's reacting with fluorine, fluorine's more electronegative than oxygen, so fluorine will take the electrons it wants from oxygen. But oxygen is the second most electronegative element in the periodic table, so if usually what it wants, it gets. So it's usually going to be a -2. Now, of course, the hydrogen, it only has 1 valence electron, right? So what's its oxidation number going to be? +1. Because remember, if oxygen takes the electrons, then hydrogen has to give them, right? Hydrogen's typically, like I said, always a +1 or a -1 when it's with other things. When it's by itself, obviously it's 0. But when it's with other things, hydrogen is going to be a positive 1 with nonmetals, negative 1 with metals. And then of these two, carbon and oxygen, which one's more electronegative, carbon or oxygen? Oxygen, which means oxygen's going to get what oxidation number? -2. And if oxygen is a -2, and there's 2 oxygens, that means that the carbon has to be +4. Because the sum, just like the total charge has, just like the total positive has to equal the total negative if it's uncharged, the same thing is true here. With ionic compounds, the same thing is true with covalent compounds. The sum of the oxidation numbers for any neutral compound has to be 0. So if oxygen's a -2 and there are 2 of them, that's a total of -4. I need a +4 to balance that out. You can also set it up like an equation. Like, for example, let's say that I had something like this. Let's say that I had SO3, okay? I can say, okay, well, 1 times the oxidation number of sulfur plus 3 times the oxidation number of oxygen is equal to 0. This is SO3. And then I could say, okay, well then sulfur, now oxygen is going to get the -2 charge. I know that because it's more electronegative. So this will be 3 times -2, and that's equal to 0, which means that sulfur -6 is equal to 0. So that means sulfur must be what? Sulfur must be +6. I just treated it like an equation. If it's easier for you to do it like this, you can. I just treated it like an equation. I just basically said, oh, what the sulfur S is my one variable, O oxygen is my other variable. I'd be like, okay, I know that oxygen is going to have a -2 oxidation number, so I plug that in for oxygen. And then I solve for what sulfur would be. This is a 0. So 3 times 2 is -6. 3 times -2 is -6. So sulfur -6 equals 0. That means sulfur must be a 6. No. Like I said, I'm pretty sure he's going to limit it to one of these very easy ionic ones. He's not going to probably give you anything more difficult than that, which is why I hesitated to bring up one of these hard ones to begin with. But you guys asked for it, just saying. Anyway, so here we go. And then if we're looking at this, here, I can see that my carbon went from -4 to +4. So what happened to the carbon? It was oxidized. And I see that my oxygen went from 0 to -2, which means that the oxygen was reduced. So, no problem.
And you said hydrogen, when it's with non-metals, is positive?
When it's with non-metals, it's a positive one. When it's
with metals,
it's a negative one. Exactly. And you'll one thing you'll notice, hydrogen, its oxidation number didn't change, right? +1 and +1. You'll have elements like that sometime where the oxidation number doesn't change. So the hydrogen was neither oxidized or reduced. All right, cool. What other questions can I help you with? 18? We certainly can. So it says a gas sample in a closed expandable container of initial volume 5 liters was allowed to warm from 25 to 35 degrees Celsius. What is the new volume, assuming that pressure and the amount of gas do not change? Now, obviously there's a lot of gas laws. If you're having trouble remembering them all, just remember this one, the ultimate combined gas law. So it's P1 D1 over N1 T1 is equal to P2 V2 over N2 T2. This has all the other gas laws in it. Now here's the thing. If anything is not changing, if anything is not changing, you can take it out of the equation and ignore that particular piece. In this case, it says the pressure and the amount of gas do not change. In that case, what two things should I ignore? The pressure and the moles, N. So that gives me the equation that I'm going to use for this, which is V1 over T1 is equal to V2 over T2. Now, at this point, what I'd like to do is I list out my variables. So V1, T1, V2, T2, and then I figure out what I have and what I'm looking for. So usually I consider the V1 and T1 to be my initials. They don't have to be, but the V1 and T1 are the volume and temperature that go together. So what's my initial volume here? 5 liters. And what's the initial temperature that goes with that volume? Yeah, 25 degrees Celsius. And yeah, whenever we have temperature in chemistry, we always have to convert it to Kelvin. What's the exception to that? When is the only time that I can not worry about converting it to Kelvin?
No, you don't ever.
You actually do. You can ignore it in one case and one case only. If it's change in temperature. If it's temperature, you must use Kelvin. If it's change in temperature, then it doesn't matter. Because if you think about it, what's the difference between Kelvin and Celsius? 273 degrees, right? So if I add 273 degrees to the initial temperature, and I add 273 degrees to the final temperature, the difference between them, is it going to change whether I use Celsius or Kelvin? No, it's going to stay the same. So when you're using change in temperature, like when you have Q is equal to MC delta T, then you don't have to worry. Then you don't have to worry about converting it. So when you change in temperature, you don't have to worry about it. But when it is just temperature, then you always have to have Kelvin. All right, so what's the final volume? We don't know, right? And what's the final temperature? 35. So now we're going to add 273 to each of the temperatures. 273 plus, yep, 298. And then 35. Yeah, 308. Now, me personally, I don't like dealing with fractions. So, if I have fractions like I do here, I'm not going to necessarily want to go ahead and plug in my numbers first. It's usually a little bit faster if I solve the equation first. And solve the equation in this case for V2. I'm looking for V2. So I'm going to go ahead and cross multiply this. And if I do, I'm going to get V1 times T2 is equal to V2 times T1. Cool? So then you're going to divide both sides by what? T1. So you're trying to get V2 by itself. So this cancels out. And then so my V2 is going to be equal to my V1, which is 5 liters, times my T2, which is, 308, divided by my T1, which is 298. And now you see, hopefully, why I wrote out my variables over here, because if you're not very careful with keeping track of what numbers are what, you could accidentally switch those two temperatures and end up getting the wrong answer, right? So Be very careful with that. Keep very close track of what your units are, or what numbers are what. Label them, write them down, list them, whatever you have to do to keep track of them. Because it's very easy to make mistakes. One of the most important qualities that is necessary to do very well with chemistry is attention to detail. Attention to detail. Okay, cool. And what do you get with that? 5.17. Yep. Now, coincidentally, if you were running out of time and you didn't have time to work this out, what's a real easy way you could kind of cheat on this one? What happens to a gas when you heat it up? It expands, yeah? So your answer is going to have to be what? Greater than 5. Now, 5, the only answers greater than 5 would be C, D, and E. But here's the thing. Is 10 degrees a big change or a small change? Small, especially in the absolute temperature scale, right? Because you have to keep in mind, you have to add 273 to both of those. So if you recognize 10 degrees is a very small change, that means it's going to be a very small increase. The only one that has a small increase is D. You could actually get away with doing this problem without ever actually doing the problem. Cool, huh? So, now, unfortunately, though this will help you to be able to do any of the problems with any of the gas laws, he does like to throw these types of questions on there, which means you still unfortunately have to kind of know the names of the stupid laws. So Charles' law is the volume and temperature relationship. But see, here's the thing: as long as you know this here, as long as you know that Charles' law is about volume and temperature, you can kind of figure it out. Well, if I increase the volume, what happens to the temperature? It increases as well. So the volume of a gas increases when the temperature increases, or it decreases when the temperature decreases. Whatever happens to the one happens to the other. Answer E. Okay. Any other? So, what question would you like to go next?
You know, like just for like the classification of the reactions, like for example, like today in class you said is oxygen is in the, I think, the product, and we know it's a combustion.
Oxygen is a reactant.
Or
yeah.
So if the oxygen is a reactant, then is the combustion.
Not always.
It's not like a funnel. Right? Like that thing, like goes into like a funnel or something.
Yeah, it all.
With a hydrocarbon. Yeah. So I actually have, and this is actually useful in the little concept review that I came up with for you guys, because I'm awesome like that and do super nice things for you. In all seriousness, I'm going to go ahead and download this and pop it up for you. So if you look at the Chapter 5 review, one of the cool things, in addition to show you how to do limiting reagents and percent yields, is type of reaction. So I just want to go over like the easy thing to recognize with synthesis reactions. So synthesis reactions, there is only one product. Only type of reaction that's going to have one product is synthesis reaction. So I'm going to underline the key thing to identify each one of these. So I'm going to use, I don't know, what's a good color? Use orange, why not? So single product. So synthesis reactions look for a single product. The reactants are usually elements. So if the reactants are only elements, that will also be a synthesis. So it depends on what he gives you. If he gives you, does he give you the whole reaction, or does he just give you the reactants? Okay. Because I used to give my students just the reactants, and I'd have them have to figure out what the products were and write the full reaction for it, because I'm evil. But basically, if there's only one product, that's a synthesis. Now, Decomposition is the opposite. With decomposition, there's only one reactant. Yeah, so a single reactant breaks down. So with decomposition, you have only one reactant. So synthesis, one product, decomposition, one reactant. Combustion reaction. Yeah, hydrocarbon and oxygen. You're going to have oxygen as a reactant and a hydrocarbon. The products are also carbon dioxide and water, but it is also possible to have carbonic acid can break down in carbon dioxide and water, and that would actually be a decomposition. The key point here is that you're burning something in oxygen, and the something that you're burning is a hydrocarbon. Okay. Now, single replacement, this is a little bit trickier, but single replacement's not too hard because it is an element and a compound react. So anytime you have an element and a compound react to form another element and another compound, that's going to be a single replacement. And typically, it's an element with an ionic compound. So something like aluminum and copper chloride, although you can have something like, you could have bromine react with copper chloride if you wanted to. But that would still be a single replacement. But an element and an ionic compound forms another element and another ionic compound. That's single replacement. Yes. Yes, it is on, and I'll actually go through that with you, but it is on the Canvas Learning Commons page. So you can access it from Canvas Learning Commons, and I'll go through the step-by-step on how to get there. But so this is actually, you know what? I'll just go ahead and do it real quick with you. So let's say you want to find the Canvas Learning Commons page. It's a little bit of a pain, and it makes me wonder why they thought that this was a good idea to set it up like this and didn't just like give you direct access in your Canvas course. But if you go to TCC, you'll see this homepage. If you click on Academics and then go down to Labs and Tutoring under Academic Help, and then you scroll down to Virtual Learning Commons in Canvas, click on that. And then here you have the online learning resources for all the different disciplines. You're going to want science. And then if you scroll down to the specific class categories, you're going to want general chemistry. And here's where you have the 1405 stuff. So up here we have our chapter, all the chapter overviews or concept overviews for each of the different types of concepts you guys deal with in your class. There's an entire library of practice problems with answer keys, and the answer keys are completely worked out so you can see. So chemical reactions and quantities, intermolecular forces and phase changes, solutions, gases, acids and bases, organic chemistry, etc. There's lots of different stuff up here. Then there's also, I'm working on the video tutorial library, that's not online yet, but there is a group of practice tests, including this one, which the answer key is included. So, yeah. And the virtual tutorial, or video tutorial library should hopefully be mostly online. I've already gotten the categories up. I haven't actually put any videos in, but I'm compiling the list. And these are screened videos. Like I actually looked at various different videos on YouTube to try to find the very best ones that I could. The ones that covered what you need to know at the level you need to know it in the most clear and understandable way. So I use a variety of different sources. I don't just throw you on Khan Academy or something like that, because honestly, half their videos are crap. But shame on me, it's true. But you'll find that the videos I'm going to put up here are going to be pretty good. And I think I have up to solutions right now, but I just have to put them onto the website. I haven't done that yet. Which, if you click here, you'll see there's nothing up there, but there will be very shortly. Hopefully by the end of tonight. Okay. So, yeah, that's how you get to that. So back to our practice test, I think. Where's the practice? There it is. Okay. Yes. 15? Okay. So in the reaction of silver nitrate with sodium chloride, how many grams of silver chloride will be produced from 100 grams of silver nitrate when it is mixed with an excess of sodium chloride? So here's the thing to keep in mind. The limiting reagent determines the theoretical yield. Let me say that again. The limiting reagent determines the theoretical yield. Whichever reaction produces less product, that lesser amount of product is the amount that you could predict will form. Okay? In this problem, it actually tells you the limiting reagent. What's the limiting reagent? 100 grams of silver nitrate. That is the limiting reagent because the excess is sodium chloride. So here's how you would do this. You would start out by saying, okay, well, I have 100 grams of silver nitrate. And it has a period at the end, which means that this is 3 sig figs. So AgNO3, that's silver nitrate. You have to come up with the formula for it, which is kind of evil. It's totally something I would do. I like that. But so now you're going to have to figure out what's going to cancel out here. Well, I'm actually only going to worry about the units first. Don't put any numbers before you put units, okay? Let the units guide you on these. So it's going to be grams AgNO3. And then and what are you going to convert that to? Moles of AgNO3. Okay, cool. So here's my one conversion factor. I'll worry about the numbers later. But now what am I going to have to do with the moles of AgNO3? Yep, so how do I do that? There you go. Oh, I lied. He actually gave you the equation, so he wasn't evil. I wouldn't have even have given you the equation. I would have just had you figure it out. All right, so then on top, what am I going to convert to? In this case, I want silver chloride, so that's AgCl, right? So so the only way to change the substance, the only way to go from one substance to another substance is a mole-to-mole ratio. In this case, what's the mole-to-mole ratio is going to come from the balanced chemical equation. We'll deal with that in just a bit. And then what's going to come on the bottom of the next conversion factor? Moles AgCl. And then you're going to convert to grams of AgCl, right? You don't need the molar mass for that. Now here's the thing. Have to make sure all your molar masses are calculated correctly, otherwise you're not going to get the right answer here. So AgNO3, silver is, I think, 107.87. Am I right? Or am I not right? I might be wrong. Okay. And then nitrogen is going to be 14.01. And then oxygen is 16, but there are 3 of them, so I'm going to have to multiply that by 3. So that basically is going to give you, if you add all those up, well, 16 times 3 is 48, plus 14 is 62. And then you're going to add that, so 62 plus 107.87, that's going to give you 169.88. If you add that up in your calculator or in your head. And that's that's what you get, right, if you put it in your calculator? Okay. So that means this is going to be 169. Sometimes my mental calculator isn't always working properly. I've been known to mess up. So I like to double check. And then, of course, the ratio here, these are all 1 to 1 to 1 to 1, right? So I'm just going to go ahead and say this is 1 mole of AgCl to 1 mole of AgNO3. And I get that from the coefficients here and here. there's a 2 in front of AgNO3, I'd put a 2 in front of the AgNO3 here, but in this case, it's only 1. And then the grams to mole conversion for the AgCl, it's 1 mole is equal to the molar mass. And chlorine is 35.45, so if I take 107.87 and I add 35.45, what do I get? .32. So then I'll put that there. And then when you calculate it, just multiply everything on top and divide by everything on bottom. Now, I know that some of you, you know who you are, like to multiply all the stuff on top, hit equals and put the answer, and then you multiply all the stuff on bottom and you hit equal and put the answer, and then you divide them. That wastes time. So you can, you can, this is a time test. You're going to have to get through this a little bit faster. So multiply everything on top. Just do 100 times, and you can skip the ones. So, but you could do the ones, you don't have to. But 100 times 1 times 1 times 143.32 divided by 169.88 divided by 1 divided by 1. So divide, divide, divide. Every time something's on the bottom, you hit divide it. You're basically separating them into 7 separate operations on your calculator because your calculator is dumb and it doesn't recognize that if you don't put the parentheses around it, it's going to divide by the first number, and then it's going to multiply by every number after that if you say divide by 169.88 times 1 times 1. So just to do it more quickly without needing to use parentheses and just to make it clear and simple, just multiply everything on top and divide by everything on bottom. Does that make sense? Sorry, I know I'm talking kind of fast. Okay, cool. But yeah, in this case, if you do this, your answer should be just a little bit less than 100, and I'm going to think it's 84.4. I'm pretty sure that's right. You can prove me wrong. Yep. Cool. All right. What else can I help you with? 21. All right. All right. So the gas sample contains 4 grams of CH4 and 2 grams of HE. What is the volume of the sample at STP? So one of the little tricks at STP standard temperature and pressure is that you should recognize that 1 mole of any gas, doesn't matter what the gas is equal to what volume? Yeah, 22.4 liters. So for this, all you have to do is calculate the moles of CH4 and the moles of HE. So 4.0 grams of CH4. Solve for the molar mass of CH4. Carbon's 12, hydrogen's 1. That's going to be about 16. And I'm violating my own rule. You always do units first, then numbers. So grams ACH4 moles goes up here. Because if you don't put the units first, sometimes you'll screw up the numbers and you'll end up making a mistake. That's honestly, I found that for most of my students in my long history of teaching and tutoring, if they just do this one thing, units first, and then put the numbers, that fixes the vast majority of their mistakes on conversion and stoichiometry. So units first, then numbers. So 16 grams of CH4 is equal to 1 mole. Done. And then I have 2 grams, right, of helium, right? Now, if you look at the molar mass of helium on the periodic table, it's about 4. I mean, you can actually, at 4.008 or whatever it is, but the truth is, you don't really have to worry about it because these numbers are going to be close enough that if you just put 4 versus 4.008, it's not going to really mess it up. So 4 grams is equal to 1 mole of helium. And so this is basically 0.5 moles. 2 divided by 4 is half, 0.5 mole. I know I'm messing up with sig figs. I know that this is, technically speaking, this is 2 sig figs. So this should be 0.50. And the other one is supposed to be 2 sig figs as well. It's going to be 0.25. So 0.25 moles. I know that doesn't look like a 2. Sorry. Now, if I add up the total moles there, it's just going to be 0.75 moles, right? So if 1 mole is 22.4 liters, how much is 0.75 moles? What would you do? But yeah, you have the idea though. So this is going to be your total amount of moles, and so you could use conversion factors, or you could just be like, okay, yeah, I'm just going to multiply by 22.4. But to show the logic of it with conversion factors, you just put moles on the bottom and then liters on top. And actually, that's one of the reasons I love using conversion factors, because this will help keep you from making those mistakes where you just accidentally flip something in your head. Because that can happen to anybody. It happens to me sometimes. But even if you understand it and you know what you're doing, it's like you're like, oh yeah, I know what to do, and then you just like throw it out there. But because you weren't thinking about it carefully enough and you weren't visualizing it, you accidentally flip the conversion factor. You divide when you should multiply. So setting up the conversion can actually keep you from doing that. So in this case, yeah, 22.4 liters over 1 mole. Moles cancels out, and that's going to give you, I don't know, like 16 liters, 17 liters. There you go. Cool? Any other questions? Yes? No. No, of course, yeah, we can do that. Oh, sorry. The OH bond in water is polar because what? Now, all bond polarity is due to differences in what property? Electronegativity. So the OH bond is polar because which one of these answers is the best? Which is more electronegative, oxygen or hydrogen?
Oxygen.
Yeah, oxygen's more electronegative. A is going to be the best answer. Because remember, electronegativity increases as you go up the periodic table, and it increases as you go to the right. So, because electronegativity is essentially the strength with which the nucleus pulls electrons towards itself when it's bonded to other atoms. So you can think of it kind of like a tug of war. So fluorine is like, fluorine is like an offensive lineman for the Dallas Cowboys, okay? And well, you know, and let's say, you know, sodium is like your little sister, okay? So if you have if you have a tug of war between those two, one of them is going to win, and it's not going to be, you know, a close call, you know? So the greater difference between electronegativity, the more polar the bond is. And if it's high enough, one will completely rip the electron away from the other. But let's say you're dealing with fluorine and oxygen. So fluorine is your offensive lineman. You know, oxygen might be like, you know, the running back, you know? Still pretty strong, right? But not as strong as the offensive lineman. So if you get a tug of war, the offensive lineman's going to win. So, so in the case where the difference isn't that big, it's still significant, but it's not that big. One is going to hold on to the electrons more. One's going to hog more electrons than the other one, and that's going to cause it to have a partial negative charge. Oxygen's going to hog more electrons than hydrogen, so it's going to have a partial negative charge. And then the hydrogen, because it's had more of its electrons taken away from it, more electron density taken away from it, then it's going to cause the, it's going to be partially positive. So I can draw you a little image to kind of like picture this. So let's say this is the nucleus for like the oxygen atom, okay? And here's your nucleus for the hydrogen atom. So if electrons were shared equally, I mean, hydrogen's smaller to begin with, but if the electrons were shared equally, this is what you might expect to see. Okay. Instead, what happens is that oxygen hogs the electrons. And so here's oxygen, and here's hydrogen, and oxygen hogs the electrons like that. So because and when I say hogs the electrons are, okay, the electrons are moving at about 1/100th the speed of light. So we're talking about faster than any vehicle has ever traveled on the Earth, okay? And so we're talking about hundreds of thousands of meters per second. So these things are like really flipping fast, okay? So there's no way to really kind of peg the exact position of an electron at any given point. It's moving around so fast. But this is just what's called a probability density cloud. It's more likely at any given moment to be around the oxygen than it is around the hydrogen. This would be the probability density cloud if they were equal electronegativities. When it's unequal, they're just going to be hang out around the other nucleus a lot more often. But they're still shared between both nuclei, are still pulling that electron. They're still holding on to it, but it's going to be more towards the one. And that's going to cause the hydrogen to have a partial positive and the oxygen to have a partial negative. And that's what that little D symbol is, the delta. It means a little partial positive or partial negative. But yeah, oxygen's more electronegative, so that's why it's a polar bond. I'm sorry, I know I went into a little bit more detail than I had to there, but I hope that makes sense. Any other questions? 32? What is the molarity of a KCl solution made by diluting 75 milliliters of 0.2 molar solution to a final volume of 100 milliliters? Okay, so this is fortunately a much easier problem than you might expect it to be if you recognize one key word in this problem: diluting. So that means you can use the dilution equation. Does anybody happen to know what that is? C1 V1 is equal to C2 V2. Sometimes it's just written in terms of molarity, because molarity is the most common concentration used in chemistry, and in which case it would just be M1 V1 is equal to M2 V2, but it can actually be used for percent concentration as well, or any concentration really. So my initial concentration is 0.2 molar. And how much of the 0.2 molar solution do I have? 75 ml. Mm-hmm. And then my final concentration is what? You don't know. I'll just put X. And my final volume is what? 100 ml. Has a dot here, so it's 3 sig figs. So then all I have to do is solve for X, divide both sides by 100, and what do I get? .15. Now here's the deal. I didn't pay very close attention to something which I really should have paid close attention to, and that is the units of volume. Molarity, you typically think, well, molarity is equal to moles over liters, right? And so typically whenever you're dealing with molarity, you always have to have it in liters. we are able to get away with not putting it in liters here because the volume units are the same. And for the dilution equation, if the volume units are the same, they'll cancel out, and it doesn't matter what unit you have, as long as it's the same unit. So you could have liters, you could have milliliters, you could have ounces, you could have grams, whatever you wanted to have as a unit of volume. You could use their gallons. As long as the units are the same, it doesn't matter what they are. But you have to make sure they're the same. And sometimes you'll get a problem where one is in liters and the other is in milliliters. And you have to convert one to the other. It doesn't matter which one you convert, but you make sure that those volume units are the same before you plug it in. Any other questions? Yes. 25? Yeah. When KCl dissolves in water, and then it has all these different things. Okay. So this is about solution dynamics. Now, when KCl dissolves in water, first of all, because KCl dissolves, which means that the ions are going to separate, right? So what causes those ions to separate? What? Electronegativity does play a role, but in terms of what particles cause those, because potassium is positive, right? And chlorine's negative, they're attracted to each other. How are they pulled apart? What's pulling them apart? The water, right? Because but here's the thing, water can't do it. Like one water molecule is not going to be enough, right? Because water just has a partial positive and a partial negative on the oxygen. But if you get together several oxygens, they get enough negative charge that they'll be able to peel off a positive, peel off of potassium. And if you get enough water molecules, you'll be able to peel off, or enough hydrogens on the water molecule, they'll be able to peel off the negative chloride. In fact, I actually have a pretty cool picture I want to share with you. Where's my cool picture? Where's my cool picture? Come now. Here. I'm going to find my cool picture. I know what it is. Cool picture. Aha. There you go. Open file. Here it is. That's my cool picture. This is what happens. The little partially positive hydrogens on the water molecules, they wrap themselves around the negative ion, and good, 5 or 6 of them or whatever wrap themselves around, and they peel it off. It takes a bit of doing. So I mean, the oxygen or the water has to be fairly, you have to have a pretty polar molecule like water to be able to do this. But that's how this solvation process works, where you start peeling apart ions. So what's the best description based on that image you just saw? What's the best description of what happens when KCl dissolves in water? K plus ions are attracted to Cl minus ions in the KCl crystal. Now that would be true if it was insoluble, if it didn't dissolve. But KCl dissolves, and it actually says it dissolves here. See? So our Cl minus ions, so Cl is minus, is it going to be attracted to a partially negative charge on the oxygen? No, because negatives aren't attracted to other negatives, right? So it's going to be D. The K plus ions are attracted to the partial negative on the oxygen. And likewise, you could also have a Cl minus ions are attracted to the partial positive on the hydrogens. So in other words, if B had said Cl minus for B, then that would have been correct. But they said K plus is attracted to the positive. Well, positive ions are not attracted to positives. Like charges repel, opposites attract. Does that make sense? That's a tricky question. You're shaking your head. Yeah. But you understand it though now, right? Because I just want to make sure. If I am not doing a good enough job explaining something such that you don't feel like you're confident with it and you understand it, make me explain it again. Because there's lots of different ways I could explain something, and I want to make sure that you'll understand it in a way that is going to stick with you. Yes. Sure. So going back to this picture here, essentially opposites attract. So to separate positive ions from negative ions, the negative ion has to have something positive to pull it away. And the positive ion has to have something negative to pull it away. In water molecules, the negative part is the oxygen. So the negative oxygens are going to wrap themselves around a positive ion and peel it off. And then the chlorine, the positive hydrogens are going to wrap themselves around a negative and peel it off. Like, because initially, like, you basically have, like, you know, your positive, 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 positive ions. I'm terrible at drawing, sorry, especially with the mouse. And then you have your negatives, 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 negatives. Okay? So it's all in like this big, huge, giant crystal with like millions of atoms, okay? So what happens is you got these little water molecules, and the negative oxygens are going to surround this positive ion here, and they're going to peel it off. They're going to pull it off. And when they do, the rest of them, it's going to leave the rest of them attached to the crystal. And then you're going to get positive hydrogens that wrap themselves around the negative ion and peel that one off. And they just peel it off one at a time. But this happens so fast that this is happening billions of times per second, like faster than you can even imagine. So it happens pretty darn quickly, but that's kind of like the microscopic view of what's happening. Does that make sense? Cool. Any other questions? I think we could probably hit one more if you want to. Yes. Uh-huh. It doesn't matter. Actually, I can go over a good example of balancing if you want. Would you like me to do that real quick? Yeah. Okay. Because balancing equations is a tricky thing for a lot of people. So let me go ahead and give you a really good example. You have copper plus nitric acid. The key to balancing an equation is to balance whatever's easiest to balance first. And the easiest element to balance, and you want to balance it element by element, starting with the easiest element to balance. The easiest element to balance is going to be the one that appears in the fewest places, in the fewest compounds. So if I'm looking at this particular equation, and this is a fairly complicated one, but maybe something that you might get, okay? So if I'm looking at this, first I want to list out my elements. So CH, Cu, H, N, and O. I do not keep the polyatomic ions together for two reasons. One, they don't always stay together. They sometimes split apart like they do here. And two, it doesn't really save you any time. So I don't even bother with it. I find it more often confuses students than helps them. So in that case, I list out the number of elements I have on each side. I have one copper here, one copper here, one hydrogen here, two hydrogens here, one nitrogen here, and I have 2 times 1, so that's 2 plus another 1, that's 3 nitrogens here. And then oxygen, I have 3 here, 2 times, so 3 here, And then 2 times 3 is 6, plus 2 is 8, plus 1 is 9. 9 oxygens here. All right, so if I'm looking at all of these different substances, copper only appears in 2 places. Okay? Hydrogen only appears in 2 places, the HNO3 and the water. Nitrogen, though, appears in how many places? 3. The nitric acid, copper nitrate, and NO2. And oxygen appears in how many places? 4. Yeah, 4. So I'm going to actually save oxygen for last. Nitrogen will be next to last. So copper and hydrogen come first. All right, so then I see, okay, I have a 2 here and a 1 here. The coefficients are multipliers, so I'm going to multiply the HNO3 by 2. And that's going to multiply times each thing here, so 2 hydrogens now. And 2 times 1 nitrogen is 2 nitrogens. 2 times 3 oxygen is 6 oxygens. Now I'm going to balance my nitrogen. Now, whenever you come across an odd number that you're trying to balance with an even number, the trick is double the odd to make it even and then rebalance. Let me say that again. Double the odd to make it even and then rebalance. So the odd number of nitrogens is on the product side, right? Which of these compounds is causing the number of nitrogens to be odd? The NO2 or the copper nitrate? So which one has an odd number of nitrogens? The NO2. See, the copper nitrate has 2 nitrogens, right? That's an even number. The nitrogen dioxide, it only has 1 nitrogen, so that's the odd number. So I'm going to double this one. I'm not going to double both. Double the one that's odd to make it even. This gives me a total of 4 nitrogens, right? Okay, so now I'm going to rebalance. So 4 nitrogens on this side, 2 on this side. I'm going to have to change this 2 to a 4. That's going to change my hydrogens to 4, my nitrogens to 4, and my oxygens to what? 12. Now, at this point, I should recognize that I unbalanced one of the easier elements, so I'm going to have to rebalance it. In this case, I have 4 hydrogens on this side, 2 on this side. So what do? Because this multiplies times each element in front of it. Yep. Yep. So now, so what do I do to balance the hydrogen now? I have 4 on the left, 2 on the right. I have to multiply it by 2. I have to multiply the hydrogen compound by 2. So that's going to give me 4 hydrogens. And how many oxygens does that give me now? So I have 2 from the water. I have 2 times 2, 4 from the nitrogen dioxide. So 2 plus 4 is 6. And then I have 6 from the copper nitrate. That gives me a total of 12. So if I balance the easiest ones first, the hardest ones will balance themselves. So that's the tactic that I use with these. I hope that helped. I will go ahead and stop this recording for now, but if you have any questions, you can feel free to ask me afterwards, and I will send this recording out to you as well. And let me know if there's anything else I can do for you.